All right, so as one last example of solving logarithmic equations in kind of a log of A equals log of B approach, so log of any base. If that's true, then A equals B. Now, I went over this the other day. You're not really canceling the log on both sides, but it kind of looks that way. So let's take a look at problem 54. Log base 4 of x plus 2 plus log base 4 of 3 equals log base 4 of 5 plus log base 4 of 2x minus 3. Okay, so, well, I can't just cancel out the logs right away because I don't have it written in this form of one log equals another log. So what I'll do is I'll use the properties of logarithms. The properties of logs say that when I have the sum of logs, I can combine them. How do you combine them? What do you do when you're combining the sum of two logs? Multiply. Good. So this is going to be the log base 4 of 3 times x plus 2 equals a log base 4 of 5 times 2x minus 3. And we can distribute these things inside the parentheses if you want. Log base 4 of 3x plus 6 equals a log base 4 of 10x minus 15. And that's fine. That's what we wanted. We wanted the log of something equals a log of something else. So at this point, according to this little idea that we used last time, and I reminded you of this morning, we can get rid of the logs. Now really what you're doing is you're raising both sides, you're exponentiating both sides with the base of 4. So 4 to this power, 4 to this power. But I'm going to skip that step. Let's just write 3x plus 6 equals 10x minus 15. This is just a little linear equation. I'll subtract 3x from both sides and add 15 to both sides. That gives me 21 equals 7x and 3 for x. Let's remind ourselves of something though. When you're solving logarithmic equations, when you get down to this point, what do you have to do? You have to check it. The very least that you have to do is to make sure that in this initial equation, plugging in a 3 does not give you any 0 or negative numbers for your logarithms. So we're okay here, 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 and here. 2 times 3 minus 3, we're okay there. So overall, we're in good shape. But at the very least, you need to make sure that you don't have anything that's outside the domain of the log function. So that's one way to solve logarithmic equations. And it works as long as all of your terms are kind of wrapped up in a logarithm. But what happens if you have something like problem number 56? So, solving logs, part 2. In problem 56, we've got ln of x plus 2, I don't know, the book wrote 2 plus x, equals 1. You can't cancel logs on both sides because there are no logs on both sides. It's just log on one side. So you're going to have to do something else. And the something else that I would suggest is this. And it goes back to our introductions to logs. If a to the y equals x, then log base a of x equals y. So these two things are interchangeable. And basically what I'm suggesting is that we rewrite our equation using exponents. Now it might make it a little bit easier to do that if you look at ln in a different way. What's the base of the natural log? Log base e.
E to the first equals x plus 2.
Good. So it's always this kind of pattern that you might see on a weather map, kind of like a funnel cloud or something like that. The base to this power equals this. So always that little whirlwind kind of pattern. If I move the 2 to the other side, I get e minus 2 equals x. Yay. And that's it. So the other part of solving logarithmic equations is to recognize that, gee, I don't have logs on everything, so I'll just rewrite it using exponents.
In this case, could you take the e and factor in 2.7? And instead of using e, could you use the value of e and get x?
Well, yeah, I mean, if you wanted a numerical value, you could do that. It'd be 0.71828, etc. Typically, yeah. I'd probably want you to leave it like that. I like exact answers, and you could. I mean, if I wanted a decimal answer, I'd ask for it. Typically, I mean, this is exact, and then 0.71828, 1828, 18, etc. That's your approximation. That's your decimal. So I probably want this. All right. Anything else on that one? Thanks for the questions, gentlemen. Let's do a couple more here. Let's take a look at problem number 62. Log base 2 of x squared minus x minus 2 equals 2. Well, it's kind of the same thing as our previous one, and that is we don't have the log on both sides. That 2 is not part of a logarithmic term. So in that case, what I'd suggest is what we did in the last one. So Michael, what would that look like if I rewrote it using exponents? Shouldn't have a log in it. It's just going to be the base 2 to that power equals this right here. X squared minus x minus 2. From here, this is just a quadratic equation. 2 to the second is 4. If I subtract 4 from both sides, I get 0 equals x squared minus x minus 6. That factors x minus 3, x plus 2. So let's see, x minus 3, x plus 2. X equals 3, x equals negative 2. We good with those? We should probably check them. All right. Now, should I throw this one out because it's negative? No. What you have to do is figure out, does that make this term negative? This is called the argument of the log function. So when I put it into the argument, does that become negative? Well, negative 2 squared is 4, minus negative 2 is 6, minus 2 is 4. Log base 2 of 4 is 2, so that checks. But all you really need to do is make sure you don't get a negative number in there. Likewise, if I put in a 3, 9 minus 3 is 6, minus 2 again is 4, so we're okay with both of these. Both of these work. Now, even for myself, I can't just look at these problems and know if one of them is going to check, both of them are going to check, or none are going to check. You just got to check them. All right, let's try a couple more here. Try problem number 68. So log base 3 of x plus 15. minus log base 3 of x minus 1 equals 2. How come I can't use the method we used the other day? Canceling out the logs. Yeah, there's no log here. I'm not going to be able to get this as log of something equals log of something else. There's no log here. So, okay, I want to do something like I did for problem 62, but I'm running into a problem there as well. I don't have just one log equals something. So what could I do for 68? How could I get just one log? Not quite the product. Yeah, quotient rule, right? So the difference of two logs becomes the log of the quotient. Now be careful when you rewrite that. That's log base 3 of x plus 15 over x minus 1. But there's just one log here. It's not log of the numerator and log of the denominator. It's just one log. Try and rewrite this now using exponents. Do the same thing we did with problem 62. Take the base to the power of the right-hand side equals the argument. Ruda, want to give that one a shot? What's that going to look like when you rewrite it? Actually, 3 to the power of 2. Good. Thank you. So essentially, I've got 9 equals x plus 15 over x minus 1. Thank you. How are you going to solve this? Yeah, you can think of this as being, say, 9 over 1, and then cross multiply. Sure. Or you just yeah. I mean, the way cross multiplying comes about is that you're multiplying both sides by the lowest common denominator. And the lowest common denominator in this case is x minus 1. So if I multiply by x minus 1 here and x minus 1 here, I get that cancellation on the right-hand side. And on the left-hand side, I'll get 9 times x minus 1. Or 9x minus 9 equals x plus 15. So I'll subtract x from both sides and add 9 to both sides and get 8x equals 24. So x equals 3. You can verify that x equals 3 doesn't create any problems for the logarithms that you have. So yeah, it's pretty good. You can actually check this a little bit more. You'd end up with a log base 3 of 18 minus the log base 3 of 2, which turns into the log base 3 of 9, and log base 3 of 9 is 2. But at the very least, make sure that you don't have any negative logarithms. All right, how are we looking on problem 68? Okay there? Let's take out our calculators and take a look at problem number 70. Some of these problems don't solve algebraically quite so nicely, but there's other ways that we can do this stuff. Problem number 70 asks us to find the solution to log of x equals x squared minus 2. We're going to do that by looking at our calculators and playing around with those. So negative 2 to 4 and negative 3 to 5 would be the window that I would suggest. Does anyone else need a calculator? What we're going to do is we're going to enter in this side of the equation as, say, y1, And for y2, we'll put in the second side of the equation. Now, how do you think that's going to help us? What do you think we're going to do? Yeah, we're going to look to see where they intersect. So log of x for one equation, and then x squared minus 2 for the other equation. The window settings are from -2 to 4 on the x-axis, and from -3 to 5 on the y-axis. And you should get two curves that look like this. Now, y is our logarithm function stopping at the y-axis. Yeah, it's not defined for negative values, so easy. How many solutions do you think we're going to get to this one equation? One, right? Just one point where those two lines intersect. So to find where those two lines intersect, let's go to the Calc menu. Hit the second button, and then Calc. And it should give you something like this. Does there look like something that might be helpful off this menu? Yeah. Yeah, the fifth one down, intersect. So you can either cursor down and press enter, or just type the number 5. Now it's going to ask you for a point on one of your curves, kind of near your point of intersection. That looks like it's close enough. Then it's going to ask for the same kind of information from the other one. You can get closer if you want to. It's not really going to make a difference to your calculator too much. And then it's going to ask for an initial guess. So just press enter one more time, let your calculator do all the work. Are you able to get about 1.47? Is that the number you guys are getting? Okay. John, did that work on yours? Okay. Oh, the window doesn't matter. I mean, you could have a different window. You should still get the same point of intersection. Yeah? Second, and then calc, and then I wanted the fifth option down, which was the intersection. And then just, kind of keep on pressing enter, and eventually it should give you that point of intersection. Cooper, did it work? Yeah. Okay, cool. All right. Let's do two more from this section. That'd be problems 84 and 86. So we've got f of x is 3 to the x plus 1. And you're asked to find the inverse function. And we'll also graph it too. But what's our first step in trying to find the inverse function? All right. Good. And then interchange x and y. Yeah. So 2. So it'd be x equals 3y plus 1. Now what? Solve for y. How are we going to solve for y? Silence. Yeah, take the log. What base for the log do you think we should use? What would be convenient? I'd say base 3. Because base 3 is going to give some nice simplification on the right-hand side. So log base 3 of x equals log base 3 of 3 to the y plus 1. There's some nice simplification that's going to happen on the right-hand side. What would that be? All right, and what do I get? What's left? Yeah, y plus 1. So those two functions on the right-hand side are inverses of each other. They're going to cancel, so I'm left with y plus 1 equals log base 3 of x. Last but not least, move the 1 to the other side. Now I feel nervous about this, so let me rewrite this as -1, -1 plus log base 3 of x equals y. Make sure you don't accidentally kind of group those two terms together. You can't take the log of that negative 1 and bring it inside the argument of the logs. So, yeah, I think I'm a little comfortable. Parentheses would be fine. Yeah, just something that makes sure that that negative 1 is not part of the argument of the logs. So f inverse of x is negative 1 plus log base 3 of x. Nice, nice. If I were to take time to graph this, what would I see when I compared the graph of f inverse to the graph of f of x, the original function? Yeah. Yeah, you're going to see two curves that are mirror images of each other flipped around the graph of y equals x. So let's see if I can Desmos. So y equals 3 to the x plus 1. And I'm going to kind of cheat here. 3, let's see, what was it? X, oh, you know what? That's not quite the right graph, is it? 3 to the x plus 1. Put it in the exponent. X plus 1. And equals 3 raised to the y plus 1. Okay, so there's your two mirror images around the line y equals x. Nice. And I kind of cheated in drawing that, but you can get log base 3 out of Desmos. You just have to use the change of base formula. Let's try one more to finish out the section. It's problem number 86. Is that good enough? So problem number 86 is kind of the same, just maybe a little bit of the opposite direction. F of x equals a log of 3x. So first step, y equals log of 3x. X equals log of 3y. At this point, it might be helpful to remember what base logarithm we're working with. 10. How are you going to solve here? What are you going to do? Perfect. It's a little bit opposite of the way we often write it, but it's still the same pattern. The base to this equals this. So 10 to the x equals 3y. Divide both sides by 3 or multiply by 1/3. 1/3 times 10 to the x equals y. And that's your f inverse. 1/3 times 10 to the x. Nice. I think I assigned some homework the other day, so let me just assign the rest of it here. For homework, try 55 through 71, 83, and 85. Don't skip those.
Professor, for 70 again, could you have two answers for that? So I wonder.
No. Problem 70, no, but problem 71 you might. I don't know. I have to look at the graphs.
I was graphing it, and it showed me it had 2 points of intersection.
Then,
One.
my calculator showed me 1 point of intersection. I don't see how there would be 2 for problem number 70. Oh, I see what you're saying. That's a good question. It's a very good question. I think you actually might be right. Let me. No, it's all right. So Lucas is saying that, you know what, there's another point of intersection here, and he's right. And the reason that he's right is because this asymptote comes all the way down to negative infinity. So if I zoomed in, I should find another point of intersection. So let's do that. The trick in zooming in is to use a zoom box. So press zoom, and then the first option is box. If you press move around, press enter, that creates a new viewing window that you can stretch out. And when you get that adjusted, press enter. Let's take a look. Yeah, I'll be darned. How about that? There is one more point of intersection. I think I'd be really careful about asking a question like that because that's easily missed. Let's see. You can find that point of intersection, second calc, first curve, enter, enter, enter. So yeah, 0.0100, etc. Yeah, well done. There is another point of intersection there. Okay. Anything else? All right, all set on section 4.5.